Hello there, my name is Ian Matthews, and today I'm going to take you through a few slides which tell us about the links between carbon and climate. It's going to focus very much on the carbon cycle and how stores and flows and transfers within that cycle help us understand the way the world works, but also then link that back to the wider questions about things like climate change as well. So, the first thing we need to know is that the carbon cycle is a natural process. And it's an example of what's called a closed Earth system. There is a defined amount of carbon within the Earth and the atmosphere, and actually all we're really doing is moving that carbon into different locations, just part of fluxes within the carbon cycle. And on the graph to the right here you can see some of the key areas where carbon is being moved between the atmosphere or the ocean or within the actual Earth's crust in the form of more rocks or fossil fuels, but also movements between these areas, between our plants and our atmosphere or our ocean as well. And there are no new true inputs or outputs from this global system. All we're really doing is moving material around within it. Now that's not true at a local scale. It's true globally, but at a local scale we might see the movement of carbon more clearly through the changing within land use or other factors as well. So at a forest scale we can change the amount of carbon that's coming in and out of a system. And actually the system has what's called fast and slow components. And again the bottom graph here is a map of the Earth, and you can see here we have what's called net primary productivity in kilograms of carbon per meter squared per year. So this is essentially how able the Earth is to draw carbon out, in this case of the atmosphere, in kilograms of carbon per meter squared per year. And hopefully you can see these brighter colours in places like the Amazon rainforest, the rainforest of Africa and Asia as well. And these are areas where we can take carbon out of the atmosphere and place it into the biosphere as well. And that's a fast component. But the movement of material, say, into the Earth's crust is a slow component. It takes a lot longer for it to occur. Now, before we get into the details of this and how we actually know how this works, I'm going to take you through some of the terminology that's often used in understanding of the carbon cycle. And there are many words that are sometimes used for the same things. So the first one is the terms reservoirs, stores, pools, or stocks. And I will try and use the word store in this case. And it's essentially somewhere that carbon gets placed or exists within the Earth system. Hence a store of carbon or a pool of carbon or a reservoir of carbon. All of these get used. You tend to see stocks talked about in terms of more sort of carbon budgeting, so the movement of carbon around and budgeting. But here we have the very simple example of the tree. The tree contains carbon. It's storing it during the tree's lifetime. This is a store of carbon at a single tree scale. But actually lots of trees can make up a forest, and the forest itself can be a carbon store as well. And we can get an even bigger scale and look at the global ecosystems, the biomes of the Earth. And within this we can see again things like our rainforest stores of carbon as well as these brighter green colours as well. And the same is true for things like the ocean. So on the far left here we have individual shells of different ocean creatures, and these are made out of calcium carbonate. And calcium carbonate contains carbon, and they are formed by taking carbon out of the ocean water itself. And actually the sediment at the base of our ocean contains a lot of carbon as well, and this can be seen as a large store of the ocean sediments. And actually if we go even further and look in longer term components, even things like our rock record, and here we have the very famous sea arch of Durdle Door from Dorset in the UK, and here this is made out of a limestone, and limestone is made out of calcium carbonate also and contains carbon. It's a long-term store of carbon. So that's our stores. There are others as well, but these are some of the main ones we need to think about. We also have movement of carbon between different locations, and these tend to get called fluxes or flows or transfers. I'm going to try and stick with the term transfer, but essentially this is the movement of carbon between different stores. Okay, and I've picked three examples here. The first on the left here, with this last green leaf with stomata, this is a photosynthesizing leaf, and during the process of photosynthesis, what we're doing is moving carbon from the atmosphere into that leaf, into the biosphere in this case. We also have things like chemical weathering as well. Here we have, well, a sculpture from an old building made out of limestone, and you can see it's become strongly weathered by the rainfall that's fallen upon it, and it has dissolved small amounts of calcium carbonate that this was made out of in the limestone and moved it from the rock here into the water system and eventually probably down into the oceans. And in this case, we can see a really nice, obvious, direct shift in carbon from the forest, which is being burnt, and during that burning process, we're releasing carbon dioxide into the atmosphere. So we have these fluxes or transfers of carbon within our system. We also might sometimes see the term sinks and sources. Now I've told you this is a closed system already, so actually there are no true new sources of carbon, but what we can see is a movement of carbon between locations, and some areas are considered a sink of carbon if they're taking up more carbon than they're actually emitting. And some are considered a source if they're producing more carbon, in that case transferring more carbon into another location than they're actually taking in. And I picked two examples of a sink and a source. Classic forest here. This forest, as it grows, is taking in carbon, building, locking it up within the trees that exist within it. Whereas on the right here, we have a volcano, and during a volcanic eruption, what we're seeing is a transfer of carbon from the rock into the atmosphere. So carbon dioxide is released as part of the volcanic eruption. And that might be seen as a source of carbon. Now, these have various sizes and scales, and they have various time scales they work upon as well. So we have to think about these being different in terms of space, but also in terms of time as well. There's a couple of things probably worth bearing in mind. We tend to think of carbon dioxide and that aspect of the carbon cycle within the atmosphere as being problematic. But actually, there's no reason why we should think of that in that form. Carbon cycle isn't inherently wrong. It has no problematic issues to it. What we're actually seeing is the movement and the flow of carbon around the carbon cycle, and that is actually essential for life. We wouldn't exist if carbon couldn't move around the Earth system. All life is based on carbon, and therefore we wouldn't exist. And so forth. Actually, what we actually need to think about is the movement and the speed of transfer from one store to another. So how fast are we transferring carbon from one store to another? Because if we change the rate of that transfer, what we find is there might be an adjustment in the Earth system and the way the Earth works overall. Now, to actually work that out, we need to be able to measure it. And it asks the obvious question of how do we measure transfers of carbon? And in those slow components of the rock record, that's really hard. It's hard to do, it's difficult to quantify clearly, but it's a lot easier using the atmosphere and atmospheric measurements of carbon dioxide. And actually, that's where we're going to spend a bit of time thinking about how carbon dioxide moves between different stores within the atmosphere and other locations as well. To do it, we need to have good measures of atmospheric carbon dioxide, or CO2. And for that, we have some what's called instrumental measures. People physically go out and measure the amount of carbon dioxide in the atmosphere. And because of that, we have what's called the Keeling curve. And Keeling was a scientist who worked measuring CO2 and set up the Mauna Loa Observatory. So the Mauna Loa Observatory is based on the volcano of Mauna Loa in the Pacific, central in the Pacific, and since 1958 the observatory in the picture here has measured CO2 through time. The reason this location was picked to measure CO2 is it's far from continents and human activities in terms of high pollution. It's also at altitude, so it tends to sit above local weather effects, and therefore you can get a reliable measure of carbon dioxide in the atmosphere. There's one small issue with that. Because Mauna Loa is an active volcano, sometimes you get spikes and difficult to understand measurements due to volcanic release of carbon dioxide in the local area. So there's a little bit of local contamination which needs to be removed. But otherwise, this observatory has measured CO2 daily, hourly in some cases, since 1958. And what does it produce? Well, it produces a graph like this. This has been produced using the website of co2levels.org, and you can see from about 1958 on that x-axis, we start seeing this pattern of CO2 release through time up into the present day. And on the y-axis here, we have the amount of carbon dioxide in what's called parts per million. So how much in the air, parts per million, is CO2. And hopefully you'll be able to see several things about this. We can see a general increase in carbon dioxide, which we'll come back to shortly. But also hopefully you can see some other patterns that go within this. And we're going to spend a little bit of time thinking about different cycles in atmospheric CO2 and what that means for the carbon cycle in terms of transfers and stores. And we're going to start really rapid changes over 24 hours of a day, think about seasons and timescales, and then much longer timescales as we move through. So, the daily cycle of atmospheric CO2 can be thought about as a transfer between different stores of carbon. Don't worry about the graph at the moment on the left here. I just want you to think about what we're moving around. And this is a fast change in carbon dioxide in the atmosphere, and we're moving it somewhere else. And actually, in these fast components, what we tend to be picking up are shifts in the amount of photosynthesis within plants or respiration within plants. So, on the right-hand side here, we have this graph. And on the y-axis, don't worry about the numbers here. Essentially, high values mean there is more CO2 in the atmosphere, and low values means there is less CO2 in the atmosphere. And we've got the hours of the day along the x-axis from midnight and back to midnight again. And you can see we have each of the 4 seasons, winter, spring, summer and autumn, classified as different symbols. I want you just to focus on summer, so these black dots. And hopefully you can see there's an increase in carbon dioxide in the atmosphere until about 4, 5, 6 in the morning. Then it starts to fall. It reaches its lowest value by about 2 or 3 in the afternoon, and then it starts to rise back up again until it goes back to midnight again. So we see this signal of high CO2 in the atmosphere overnight and low CO2 in the atmosphere, relatively speaking, during the day. And what we're seeing there is the movement, the transfer of carbon from the atmosphere to the biosphere during the day in the form of plant photosynthesis. So plants are taking carbon actively out of the air during the day, but at night their respiration is returning some of it back into the atmosphere. So we're seeing a daily transfer of CO2, of carbon, from one store to another. Now, you might say, well, why do we have differences between the different seasons? Well, this was measured in southern England at Royal Holloway, where I work. And what we can see here is a change in the peak and the low values between summer in the black dots and winter in the clear squares here, or the white squares. And what we're really seeing here is a difference in the growth season and daylight in plants. So we're seeing much lower values of plant activity in winter than we are in summer. And therefore, there's far less of a change between night and day within those signals. Okay, so that's a very rapid transfer between different stores of carbon. Actually, we're back to the Keeling curve here. There are also annual cycles of changes within carbon dioxide in the atmosphere. And on the left-hand graph here, you can see we go from 2015 through to the present day. And hopefully you can see this is the Mauna Loa Observatory, the Keeling curve, changes through time of peaks and troughs. This is a classic sort of what's called sawtooth pattern within our data. Something odd here, this might be one of the volcanic spikes, for instance. But again, we see this pattern back through time. And it seems to be fairly regular. And in fact, it's fairly regular on an annual basis. And if you look at the graph on the right here, for the year of 2021 to coming into the present day, you can see a rise in CO2 in the atmosphere until about May, and then a collapse and fall to lower values. And we're talking about 5 parts per million, roughly. It's sort of late spring, summer and autumn. And then a return to higher values. And what we're seeing here is the movement again of the transfer of carbon between plants in the biosphere and the atmosphere. So in autumn and winter, we're starting to release CO2 from plants as they decay and decompose and still respire, and they're actually putting CO2 back into the atmosphere. During late spring and summer, we get an increase of growth in plants in the northern hemisphere. And what we then see is a drawdown of that atmospheric CO2 into our biosphere. So there's transfer between the biosphere and the atmosphere over annual scales as well. That's fine, but actually there are other processes to do with the carbon cycle which you're probably far more aware of. The carbon cycle, unfortunately, has become slightly disrupted for the short term, or we have, in fact, where I should probably put this is increased the transfer of carbon from some stores into places like the atmosphere and the ocean. And this flow diagram here basically is trying to talk about how we're moving carbon between different stores. The black is the amount and the red is the flow between these two by human activities. Okay, so the red here is what humans are doing to this actual system. And particularly things like fossil fuel burning has changed the transfer of carbon from what I'm going to call here the rock record, but fossil fuels, into the atmosphere. And that's also then been moved into places like the ocean as well. So what humans have done to the carbon cycle is they've taken something which is sat in a slow component, a very slow old store of carbon, and they've rapidly moved it into the atmosphere. So they've caused a transfer of carbon at a speed that maybe isn't naturally occurring in most cases. Now there are some natural ones on this diagram. You can see volcanoes here, but they contribute so very, very small amounts of carbon into the atmosphere because they erupt very infrequently in very short periods of time. We have things like rock weathering, as I talked about earlier. Again, a natural flow. But things like fossil fuel burning and land use change are these new transfers between the stores in the earth into the atmosphere and also the ocean. And obviously the reason we're doing this and burning fossil fuels at quite an alarming rate is due to energy provision. The burning of fossil fuels within certainly transport, but also within energy generation for electricity or heating in terms of gas, is taking our stores of carbon in the earth and adding carbon dioxide into the atmosphere. But it's not the only source. About 10% of human emissions are actually down to land use change, particularly deforestation, drainage, and agricultural purposes as well. That's about 10% of that. And what we're seeing here is a change in the landscape, which then leads to the release of carbon. And here we have some examples of land use change leading to the transfer of carbon from one store to another. Hopefully you can see from this top left image we have this field which has some gullies forming within it, and these gullies are eroding the soil and taking carbon from within that soil and removing it and taking it into the watercourses and away from this location. And that's sometimes accelerated by things like drains being cut within the fields to try and stop flooding, but again acting as very rapid transport pathways from carbon in the soils into this and then into local watercourses and eventually the ocean. But also what we see is movement of carbon in a more obvious way, in some cases through land use management or change. The bottom left here we see an image from the Scottish Highlands, and what we see here is the burning of heather moorland to try and control and allow it to be managed. But what we're actually seeing here is the taking of carbon from within the biosphere and the movement of it into the atmosphere. And that can be even more obvious. We have things like deforestation. As we can see here, this is a large forest which is being removed and cut down, taking the carbon from that forest and moving it again, ultimately into the atmosphere. And if we return to this slide, we can think a bit about where that's actually moving and how it's actually moving. And here you can see the evidence of things like fire and deforestation on the landscape is taking carbon directly, adding into the atmosphere. We might have fossil fuel burning, again, taking carbon from long-term stores and placing it into the atmosphere. but there's also a flux of that atmospheric carbon back into our oceans as well. So a lot of our carbon is absorbed back by vegetation, but also into the ocean water itself. The rest being remaining within the atmospheric store over the sort of timescales we're talking about. As a consequence of that shift of carbon dioxide from the atmosphere that we have released at an accelerated rate is this transfer of carbon from the atmosphere into the ocean. The ocean takes up a large amount of that carbon. And actually what happens is we see an interaction of carbon dioxide within the water to form carbonic acid. So you end up with a chemical formula of H2CO3, a carbonic acid, a weak acid. And that has an impact on what happens with our water body. So actually, on the left hand of this graphic panel here, we have a sort of ocean conditions pre-industrial revolution in the Northern Hemisphere, and a seawater acidity or pH of just over 8. There's still some interaction between carbon dioxide in the atmosphere and the ocean, but essentially it's fairly well balanced. When we move into the industrial period, and this is a projection from 2100, what we see is an enhanced amount of carbon dioxide in the atmosphere increases the transfer into the ocean. We have more carbonic acid in the actual and bicarbonate within this as well. That gives us fewer carbonate ions, and what that actually means is we get fewer, smaller and potentially weaker what's called calcifers or calcifiers. And these are our shells. Anything that produces calcium carbonate as part of its life pattern. So things like snails or mollusks, as they should really be called, within our ocean, our corals, and some of our microscopic marine life as well, all use calcium carbonate as a sort of exoskeleton form as well. And actually, if you want to see what that looks like, on the left-hand panel here we have a series of shells exposed to different amounts of pH. And on the left, this transparent, very smooth looking shell is absolutely perfect for understanding what it should have in terms of good ocean conditions. But as the ocean becomes more acidified, the shell becomes rather cloudy or irregular structure. The actual whorls within it become weaker to see, and we weaken and potentially reduce the ability of that animal to survive. However, a large percentage of the carbon that we have transferred from long-term stores within the Earth into the atmosphere stays within the atmosphere. And this is where we come into this fast movement and transfer of carbon into places which can then lead to a consequence to the Earth system. So actually, carbon dioxide is a powerful, what's called greenhouse gas. That means it traps heat within the Earth's atmosphere, and therefore the more of it we have in the atmosphere, the more heat that gets trapped from the sun ultimately, and therefore we lead to a heating of the Earth if we have more carbon dioxide in the atmosphere. So the transfer from the stores in the Earth to the atmosphere very rapidly might ultimately lead to a heating of the Earth's surface. And this is the theories behind things like climate change. We can try and test this and think about this. We could use the Keeling curve as a start point. Do you remember right back when we introduced this, I talked about how we could see a general increase in carbon dioxide from 1958 to the present day. And that's what you can see on the right-hand graph here. We've got carbon dioxide on the y-axis to the left, from 300 to 500 parts per million. We have time on the x-axis from 1958 here to the present day. And you can see this blue line is carbon dioxide. And it rises from somewhere down about 320 parts per million up above 400 parts per million. And on the same time, we have a measure of temperature in this grey line here. And the scale for that is on the right-hand side. And it's represented as what's called a temperature anomaly. So to try and understand whether it's warming globally, we tend to use what's called temperature anomaly charts rather than absolute temperatures. And what they do is take a reference period before the Industrial Revolution, when they know temperature was fairly stable, and they say that's essentially zero, that's our average of temperature, and they look at the temperature since then and how it has changed as what's called an anomaly plot. So we see a change in this case of about 0.8 to 1 degree warming from the initial period to the present day. relative to that sort of pre-industrial, the pre-transfer of carbon from long-term stores into the atmosphere. However, it's a fairly short record. It's not a huge amount of data. What we really need is to be able to extend that record so we can understand actually what might happen in the future, what might happen in the past, and what the carbon cycle means for understanding this. So we need to look in other places to tell us a little bit about carbon in the atmosphere in the past. We can't do that from measurements because they didn't exist. No one went out and measured atmospheric carbon in the same way the Keeling curve does prior to 1958. So we need to use something else. And the thing that we often use is something called a proxy. A measurement that we couldn't go and measure ourselves and physically stand there, but we could go and take a sample from something that tells us what that carbon dioxide content was. And in our case, what we use in this case is polar ice cores. So in both Greenland and Antarctica, we have large ice caps, really thick ice down to about 3,500 meters thick. And what that is a record through time of that snow accumulation. And we've got some images here of ice cores being extracted, fairly shallow ones in this case. So we've got a drilling rig and people working on the ice in Greenland. And here we have another drilling rig. And this is a cylinder that pushes down into the ice, some hundreds of kilometers, and extracts these circles called cores of ice. And actually, if you go deeper and deeper and deeper, they get older and older and older. And we're able to actually work out the conditions at the surface of these areas in the past. In many cases, they're almost like tree rings. So we see bands within the ice representing individual years of snow accumulation, which means we can very precisely work out what's happening in the past. Sometimes we find evidence of volcanic eruptions, which is what this dark black line is in this ice core here. But actually, in the terms of carbon, what we're really interested in are tiny bubbles contained within the ice. So this is a disk of ice, one of these long cores cut through and a disk extracted. And hopefully you can see all these tiny dots within it. These are all bubbles of air that were captured when the ice formed. So you imagine when it snows at home and after a few days the ice gets compacted down, and actually, although you can't see it, there are tiny gaps within it which form little bubbles of air. And those bubbles of air contain tiny amounts of the atmosphere when that ice core was formed. So if we can extract and measure carbon dioxide within those tiny bubbles, what we can do is work out how much carbon dioxide there was in the atmosphere in the past. And this has been very successful because we can actually in Antarctica find ice cores which go back 800,000 years into our Earth's history. And they all contain these bubbles of air which include things like carbon dioxide within them and are little time capsules, little tiny things where we can actually measure the amount of carbon dioxide in the air in the past. And if we do that, we can get quite a clear pattern. So you can hopefully see here a carbon dioxide on the y-axis graph, and then on the x-axis we've got time in thousands of years. So this 170k is 170,000 years ago, and this is 771,000 years ago. And hopefully, if you just focus first, this is the present day. So we are currently somewhere above 400 parts per million of carbon dioxide in the air, and this blue line tracks carbon dioxide in the atmosphere over the previous 800,000 years. Hopefully, what you can see is naturally, over these last 800,000 years where humans weren't burning fossil fuels or undertaking deforestation, what we can actually see is that the values of CO2 vary from about 180 parts per million to a maximum of maybe up to about 300 parts per million. But actually, human activities has pushed us over 400 parts per million. So we're in a unique situation that hasn't occurred at any point in the last 800,000 years. Now you might also be looking at these peaks and troughs. They look a little bit like the cycles that we see in our annual cycles in CO2, or even a little bit like the daily cycles. And actually what these are picking out are big changes in the Earth's surface conditions. So in these low values of CO2, we are having ice ages, lots and lots of ice on the landscape of the Earth. And in these high values, we're having warm periods like the present day, where we have lots of forests. So again, what we're seeing here is a transfer of carbon into the biosphere and in the atmosphere through plants. So we can see long-term shifts, but none of them match up closely whatsoever to the current values that we have. And of course, remember, what we're trying to do here is validate the idea that we can use this information to understand temperature as well. And we can. So if we put temperature data for the same time period and overlay it with this is what we get. The same blue graph is our carbon dioxide measurements in parts per million back to 800,000 years ago. Now, hopefully what you can see is this black, rather thick line on here is our temperature data set. We're right up here. We've just moved into this area. Okay? And actually, yes, there are phases in the past which are thought globally to be warmer than the present day. There are also cold periods where our ice is dominating as well. But actually, you hopefully can see this blue line up here is our carbon dioxide. And what we don't understand now is how doubling carbon dioxide in our atmosphere essentially might lead to a change in temperature in the near future. We have lots of models to predict it, but actually that it's an ongoing area of research as well. So, what about even further back in time? What about how do we understand what the Earth might look like under different carbon dioxide conditions? Well, although the ice cores run out at about 800,000 years ago, there are other ways of looking at this. We can use chemical data and fossils from plants and things that live within the ocean to understand carbon dioxide further back in time. So I'm going to spend a little time explaining this graph, which is from Ray et al. 2021, the reference for this, and you can get it from this link down here. Here we have on the x-axis timescales, and here we are in the common era. So this is our modern day, it's the industrial revolution up to the present day here. There's a little break in the scale, and now we're into thousands of years between about, well, almost the present day back to 800,000 years. That's our ice core record of gases. And then we can go even further back in time using our other data to get us back as far as 60 million years, just after the dinosaurs disappeared. So how about trying to understand where we are in terms of carbon dioxide content further back in time? So we know that none of this data gets close to the modern values brought about by the Industrial Revolution. However, what we do know is that in the past there were higher carbon dioxide levels. So here, hopefully you can see an increase in carbon dioxide further back in time. In some cases, about 50 million years ago, as high as 2,000 parts per million in the landscape. So we can go further back in time and see different conditions. And there's a few annotations here talking about things like beech trees in Antarctica about 5 million years ago, or alligators in the Arctic 40 million years ago, which give us indication that maybe when we change the amount of carbon dioxide in our atmosphere, what we do is change the surface conditions considerably. Actually, this is really important because when we look at the predictions for future climate change, this is what we see. There are 3 scenarios presented, something called scenario 8.5, which is sometimes called the runaway emission scenario, where we just continue burning fossil fuels at the rate that we already have done, and it leads to possible carbon dioxide contents in the atmosphere of 22,000 parts per million, something not seen for about 50 million years. And then we have some more restrained estimates that are based on cutting carbon dioxide as quickly as possible out of our system, cutting carbon away and burning of fossil fuels away. And here we see conditions might be reached that haven't been seen for 5, 10, maybe 20 million years on the Earth's surface. So what we're doing is we're shifting carbon dramatically and very rapidly from long-term stores into our atmosphere and producing conditions not seen on the Earth's surface for millions of years. Now, one might assume that has an impact on the conditions and the climate that we're working within. And you'd be right. And I've taken this example from Burke et al. 2018, and this is a paper which talks about actually temperature trends through the same time period, going back to 60 million years and thinking about predictions. And here we are looking at basically the modern historical data set. So here's 1958, here's the Keeling curve, here's the warming we can see to the present day within it. Here is our ice core record going back to about 800,000 years. Again, the scales change along the basis, so be a little bit wary of this, into years, thousands of years, and then millions of years as well. But we can go further back in time again and go back to 60 million years here, and hopefully you can see when we get back beyond our ice cores, we see a much warmer world, values of above the modern values by 5 million years ago, by maybe 5 degrees warmer globally by 20 million years ago, and then possibly as much as 10 to 15 degrees warmer 50 to 60 million years ago. And this is driven and linked very closely to those changes we see in CO2. And then if we put our scenarios back on, what we see is that high scenario, the 8.5 scenario up here, gives us temperature rises not seen since about 20 to 40 million years ago, potentially, whereas our lower emission scenarios restrict us to something which might have been more like 3 to 5 million years ago. But actually, a significant change. We've caused a long-term shift in the amount of carbon in the atmosphere and the oceans, and that has then led to a change in the Earth's conditions and the warming of the Earth's surface as well. So what might this mean overall? Well, firstly, we see these very high values, and it will give us potentially a hotter world and probably a break to those natural cycles of glaciation, these ice ages I talked about as well. What it doesn't mean is the end of the world. What we're not seeing here is a shift which will cause the end of the world. It's essentially just an imbalance within that carbon system, and over time it will take a while, but we will actually remove the carbon from the atmosphere into the ocean, into the sediments, into the rock record, but it will take a very long time for that to occur. And people have tried to model this. What we can see here is a modelled output trying to show what might happen to the Earth in the future. And this is based on that very high emission scenario, the 8.5 scenario. And what we have here is temperature, represented by colours, against pre-industrial, so blue being cold and red being warmer. And what we see is that when we warm, in the present day, we hit CO2 levels well above 1,000 parts per million, with global temperatures maybe as much as 9 or 10 degrees warmer than present. And it continues to be that warm for about 200,000 years. It takes that length of time for the global Earth system to remove the excess carbon dioxide from the atmosphere. It takes about 200,000 years to try and remove it. What that means is we have elevated temperatures for a long period of time. And only when we start getting to these blue colours, 200,000 years and later, that we start to see a resumption of the natural patterns of climate within the Earth system. So what consequence might that have? Well, we might see the removal, or certainly the severe reduction of ice in Greenland, a much smaller and thinner ice cap over Antarctica, and the removal of ice from around the other parts of the world. These dark red colours are meant to represent where it's the warmest. You can see almost everywhere is universally warm across the globe in that period of time. So the next question really, and probably the last thing we can deal with, is how do we actually think about what we can do to try and remove or change those transfers of carbon between stores. And this is where I'm going to leave you actually on this slide, is I'm going to finish here to get you thinking about actually how the carbon cycle and the carbon system can think about transfers between different stores and how we might change activities. Ideally, we need to stop putting extra carbon into the atmosphere. So ideally, what we would do is stop burning fossil fuels, and as quickly as we possibly can, because that is a transfer of carbon that is taking it from a very slow, very deep, old source and putting it into the fast components of our atmosphere. and that's difficult to then remove reliably. But there are other things we can also do. We can plant trees. It might seem a very basic thing, but hopefully you can see that the annual cycles and the long-term cycles of transfers between the atmosphere and the biosphere are quite important. And therefore, being able to plant trees and and encourage the biosphere to take up carbon is an important way of removing atmospheric carbon, and it's a fast way of doing it as well. Individual trees don't live very long. In the grand scale of what we're talking about elevated carbon dioxide levels for as much as 200,000 years. Actually, planting a tree that lasts for 100 or 200 years isn't that useful. What we need to do actually is to plant forests and keep them. So the carbon stays within the forest, and the various trees that grow and die in the next generation of trees store that carbon over a much longer term. That's a brilliant way of taking carbon dioxide from the atmosphere and locking it up in the biosphere in a longer term. There are some technological solutions. The idea that we can take the CO2 that we're generating within our industrial or power generation, and we can try and lock it up somewhere. And there's been lots of effort to try and what's called sequester carbon, so locking up the carbon in places like the rocks. So trying to pump carbon dioxide down into the rock strata and actually keep it locked away. It's quite a high-tech solution, it's quite a lot of money, but it's something which could potentially take carbon very rapidly. And then lastly, the one I'm going to leave you with is one we probably don't think about, is the restoration of wetlands and looking after our wetland areas. So a wetland, a peatland, essentially is a massive store of carbon. And due to land use changes, what we've tended to do is to drain these, degrade them, or even just trying to remove them entirely. Actually, if we leave our peatlands on the landscape, what happens is the plants that live on the surface take up carbon, and they live and they die, but because they're waterlogged with high water table, they survive essentially and are preserved through time. And that carbon gets locked away. And that's a long-term store of carbon, thousands of years, that essentially can very actively pull carbon out of the atmosphere and lock it into the biosphere, and then lock it away as peat for a longer period of time. So it's a very rapid drawdown of carbon, but a longer term store of carbon as well. And that's what I want you to think of, the idea of catastrophic climate change, this idea that we might rapidly heat the earth and cause it to be very difficult for humans to live successfully, actually is a problem of the carbon cycle. We need to draw carbon from one store into another to try and restrict the effects of the greenhouse effect of carbon dioxide and that heating of the Earth's surface as well. And I'm going to leave it there. There are some activities you can look at as well, which will help build on some of the information that we've talked about in this lecture.